Okay, so today is the first session of the new course this semester called Triangular Prism Equation and Categorification. Okay. So today we will introduce the topic. So this course will cover a paper, in fact, with the same title by Zhengwei Liu, myself, and Yunxiang Ren. So this course will cover a paper entitled as above by Zhengwei Liu, myself, Sébastien Palcoux, and Yunxiang Ren. So the paper called Triangular Prism Equation and Categorification. Okay. So the paper is available in the reference of the course. See, reference in the web page of the course. Okay. So what this will be about? Okay, so this course will be about categorification. It will be about the categorification problem of fusion ring into fusion categories. So we will briefly recall the definition of a fusion ring and fusion categories, but for more details, you should see the web page where you can, there is a link to the last semester course, video and slide, in particular the beginning, where we review all the definition in details of fusion category, etc. So from here, in fact, I did that. So the four last semester, we review in details this definition. For this semester now, I will no more review in details that. But if you did not attend the previous semester, you just go to the web page of the course and you click on the video and the slides of the first session of last semester, and we will have a full review of this definition, so it's okay. Okay. So the topic of the course is the categorification problem. Categorification problem of fusion ring into fusion categories. To fusion categories. So write this here. So don't worry. We will briefly recall their definition. Briefly recall their definition, but for more details, you see what I said before. In fact, for the fusion ring, the notion of fusion ring is quite easy, so we can define it in full details. It's very quick, but for fusion category, it will be not in details. So I send you back to the last semester's material. So for more details, see last semester. That course. And no, so the book tensor category by Gelakinici Shostrik in reference also. So you don't need, in fact, to follow this course, this current course, you don't need to attend the full course last semester, but just the beginning. You just read the beginning, and you will have the definition details. So we recall what is a category, what is a monoidal category, etc., etc. I will not do that here in details. Okay. Okay. So, categorification problem of fusion ring into a fusion category. So, which means the existence of a solution of the system of Pentagon equation. So, existence of, so I put into parentheses invertible, because there is an invertibility assumption. Solution of the system of Pentagon equation. So if you remember, the system of Pentagon equation. So I will denote the system PE like that. So we will see this system of Pentagon equation in full details in this course, because this is the main point of this course, to reformulate the Pentagon equation system pictorially. So here I don't need to recall the definition in this introduction part of what is a Pentagon equation. We will see that in full details later. Okay, so for those who, for people who don't know what is Pentagon equation, let me just mention here that this system is usually too big to be solved directly. Usually, this system is too big to be solved directly. So this is the main point of this result, of this research, to find other way. Okay. And our way is pictorial. So the main goal of this course is to prove a pictorial reformulation of the system of Pentagon equation. Is to prove in details a pictorial reformulation. And when we say pictorial, it's pictorial reformulation of the system of Pentagon equation in it like that. And when we say pictorial, this is I mean it will make sense in category theory. It's not just ID. So let me write it like that. Making sense in tensor category theory. It is not just picture like that to provide ID. It is a pictorial which makes sense, really sense, which makes sense in tensor category theory. Okay, so, and this pictorial reformulation, in fact, will provide some insight to manage the complexity by localization. So let me explain what I mean by that. So providing insight to manage the complexity by localization. So I will explain what I mean by all the words in this sentence. By localization. Localization. So let me write that. Manage complexity localization. So what does it mean? What does it mean? Okay. So it means the following. So as I said, the Pentagon equation is too complex to be solved directly. It's too complex to be solved directly. So complexity is in the sense of complexity here is in the sense of complex here when I wrote yeah, it's too big, too complex to be solved. So we need to do some, we need to find another way. So we need to manage this complexity. So directly, okay. So we need to manage. So this complexity need to be managed. Should be managed. Should be managed. Okay. Not this one. Okay. Anyway. And our approach is by localization. So I will explain what is localization. Our approach by localization. Localization. Okay, so what I mean by localization, which mean by finding small subsystems which can be solved directly. So we have a big complex system, and our approach to manage the complexity is to find small subsystem with as less as variable as possible. Small subsystem, which means can by finding. And I guess I will have time today to provide the idea how we can do that using our pictorial reformulation, which means by finding small subsystem which can be solved directly. Can be solved directly. And in fact, ultimately, that this will not be the point of this. This is not the point of this paper. It will be for coming research. coming work. So ultimately, in fact, you provide an increasing sequence of subsystems. So you start with a small subsystem you can solve directly, and then you increase a little bit, and step by step you can solve directly, step by step, and ultimately you can finish, you can cover the full system. So this is the goal, in fact, of this research way, but this will not be the goal of this course, of this paper. This course will focus only on the first step, how to use symmetry of a pictorial reformulation to find the first step. So the first subsystem, the smaller one, so ultimately an increasing sequence of subsystem. But as I said, here we will only focus on we will only consider the first step, the starting point. We will only consider the starting point, and by starting point I mean the first subsystem of the sequence. Okay, so let me check the time. Okay. So as usual, we will have 5-minute break at 4, between 4:05 and 4:10 p.m. So it's after 20 minutes we will have a break. Okay. So now the question is the following: how our pictorial reformulation can find small subsystems? And so I will need to explain, provide the idea of the pictorial reformulation. How our pictorial reformulation can find such small subsystem. So let me explain. In fact, so considering the as I said, the full system of Pentagon equation is too big to be solved directly. So usually in the literature, people, the researcher, mathematician, never consider the Pentagon equation directly, except for very specific case, as a pointed case or near group case or something like that. Otherwise, for usual case, people never consider the Pentagon equation directly because it's too hard to solve. And so our approach is quite new in the sense that we want to deal with this system. So we accept to deal with this system, and we are looking for a strategy. The direct strategy, the brute force strategy cannot work, so we are looking for a smart strategy which can work at least for more cases than, as I said, pointed. And in fact, for the near group, we may mention, in fact, a work about near group using this pictorial reformulation. So what I wanted to emphasize is that this is quite new. This approach is really new to consider the Pentagon equation directly with a smart strategy. And this will be useful for some application we will mention later. So So how our pictorial reformulation can find such small subsystems? So the idea is to use symmetries of the pictorial reformulation. So we have a picture, and this picture has symmetries. And so if you use the symmetry, otherwise, if you can find some insight. Otherwise, if you just consider the Pentagon equation without reformulation, you don't see the symmetry. The symmetry are completely hidden. But when you reformulate pictorially, you see symmetries, and then everything becomes more clear. So by exploiting the symmetries, let me write. Let me use another color for that. Symmetries of our pictorial reformulation. Of our pictorial reformulation. In fact, these symmetries exist in the Pentagon equation, but they are not visible. The pictorial reformulation don't create symmetries, they just reveal symmetries. The pictorial reformulation does not create symmetries, but reveal them. Okay. So now we need to provide the idea of this pictorial reformulation. So more precisely, so as we will see in more details later, of course, we will not provide all the details in this introduction part, as we will see in more details, in full details, in fact, later. The system of Pentagon equation, so PE, is a system of the form like that. So I will explain the notation. Equal sum star star star, where each star corresponds to represent a variable. So they are not the same variable. So represent a variable. So you have several variables, but every variable is represented by this symbol just to explain, just to provide the ID variable. So the Pentagon equation is a polynomial system. Of degree 3. So you will understand why I wrote this shape, this form. So here you have 3 variables, and here you have 2 on the left-hand side. You have 2 variables, sum of multiplication of 2 variables. On the right-hand side, you have a double sum of a product of 3 variables. Okay, and in fact, so here you have a double sum because, in fact, we will sum over we will sum over object and morphism. Whereas here we only sum over object. Okay, so but I don't go into the details right now. So our pictorial reformulation replace each variable denoted star here, and also called in the literature, they are usually called F symbol, by a labeled tetrahedron. So I put labeled into parentheses because I will not label the tetrahedron in this introduction part. I will provide the tetrahedron without label. But when you go into the details, of course, you need to label the tetrahedron with object and morphism. So we've labeled tetrahedron. Okay. So it will be labeled, not today, but when we will explain the details, by object of the category, object and morphism of the category, and morphism of the hypothetical category, because we want to categorify a fusion ring. So we want a solution of the Pentagon equation, an invertible solution, as I said. But such a solution don't necessarily exist. So we are considering an hypothetical category. So some hypothetical object and morphism of this fusion category. So we assume it exists, and then we can formulate this Pentagon equation and this pictorial reformulation. So by object and morphism of the hypothetical fusion category. So it may not exist. So if it does not exist, then we will get a system without solution. So we get a contradiction. You assume the fusion category exists, you get a system, you get a subsystem by our approach, and in fact, no solution, so contradiction. Contradiction, this fusion ring cannot be categorified. It cannot be written as a category with object and morphism, satisfying all the good properties. And in fact, in the application, we will we'll provide full details of a very important example of a simple integral fusion ring, which is excluded by this method and only by this method. We don't know any other method excluding it. Very hard. Okay, so tetrahedron. So let me draw the tetrahedron. I will draw it, as I said, without label for today, because it's so here is the tetrahedron. So you can see it as a graph. There are several ways to see it. You can see it as a graph with vertex and edge. Wait, this one. Marche plus tout ça. Chiant. Anyway. Okay, so you can see it as a graph. So with vertices and edge. So I never remember vertex, edge. So this is edge, and this is vertices, if I'm not mistaken. Okay, and so you can also see it as geometrically. You can see it as a pyramid. So it will be labeled. In fact, we will label every edge. Every edge we will provide some label, and every vertices also will have a label for each vertices, but we will not mention that for now. So you need to label. Okay. So we do not label it in this introduction part, but it will be in the main part. It will be later. Okay. I just want to explain the idea of this reformulation, and for so we don't need the label, just to explain the idea. Okay, so each variable is replaced by a tetrahedron like that, and each equation is replaced, reformulated by two ways to evaluate a triangular prism, a label triangular prism with label tetrahedron. Whereas each equation of the Pentagon equation system reformulate as two ways to evaluate a labeled, so as before, a labeled triangular prism. Triangular prism by label tetrahedron. Label tetrahedron. Or tetrahedra, if I am not mistaken. Okay. So let me draw the picture. In fact, I will draw two pictures. What I mean by that. So you start from a triangular prism. So the graph, so as I said, this is a graph of a tetrahedron. You can also see it geometrically in 3 dimensions as a pyramidal. I will draw the graph of a triangular prism, but you can also imagine it geometrically in 3 dimensions. So the graph is the following. You have two triangles, one inside the other. And so you have the vertices and edge like that. So this is a graph of a triangular prism. And you can imagine it in 3 dimensions. So it's like a tube with a slice of triangle. So you have a kind of tube like that. Like that. So this one will go there. Like that and like that. So you have a cylinder with a slice is a triangle, like that. So you can visualize it like that, as this graph. And so this is the triangular prism. Triangular prism graph. So of course it should be labeled, as I said. So again, of course, we will need to label every graph. Okay, and so the idea here is, so you have two ways to evaluate. So one way to evaluate will be like that, a sum of variable like that, labeled one, on one way, and the other way will provide a sum like that. And so and after the pause, we will explain. In fact, there is a Dylan Thurston provided, in fact, in a paper about topology and graph theory, he provided a way to understand the idea of the proof on how to evaluate the triangular prism in these two different ways. So this equation is called, so this is tetrahedron. So it will be called Triangular Prism Equation. Triangular Prism Equation. And the system will be noted TPE, like that. And so just for this is a tetrahedron. Tetrahedron. Okay, so we will make the pause now. And after the pause, we will understand the idea how to prove the triangular prism equation. Pause. Okay, so before explaining the idea of how to prove the triangular prism equation, let me explain why such pictorial reformulation help in our localization strategy. So, how such pictorial reformulation help for our localization strategy. Localization strategy. Okay. So first, so as I said, a triangular prism and a tetrahedron are two geometric objects in 3 dimensions which has symmetry when they are regular. So note that a regular tetrahedron or triangular prism has a symmetry group, as a so we consider orientation preserving. For now, orientation preserving symmetry group. So the alternating group A4 for the tetrahedron and the cyclic group C6 for the triangular prism. So you can see the symmetry. For example, you can rotate like that, or you can you have some mirror image, etc. So you can. So here, mirror image is not orientation preserving, but anyway, you can play with the symmetry, and you can see this symmetry group. So, in fact, the triangular prism equation can be considered up to symmetries. Can be considered up to symmetries, up to these symmetries, which, so when you do that, you reduce the number of equations and the number of variables, but it's not enough, of course. Well, even if you do that, the system is still too big, but it's the first step. And we will see the main point next. So, which already simplified the system, but as I said, the main point next. So the main point here is to choose. So you have a nice symmetric pictorial reformulation, and the main point here is to choose an appropriate labeling. Next, the choice of an appropriate labeling. So of course, if you consider all the possible labeling, you will get all the equations of the system. So you will get the full system. But what we want is subsystem, small subsystem. And in fact, you will get small subsystem by choosing an appropriate labeling. And appropriate labeling. Keeping some symmetries. So the choice of an appropriate labeling keeping some symmetries permit to get a subsystem minimalizing the number of variables involved. Permit to get a subsystem minimalizing, or to get subsystems, in fact, not necessarily one. You get subsystems minimalizing the number of variables. Involved. Okay, so you have a nice pictorial reformulation with symmetries like that, and you can play, of course. Here, we only need to label, so you can play with this picture. You can, okay, I will label this one with the same label, and this one, another label the same, and and again you will choose some label for the here also. You can label this one the same, and this one with something else. So you get something symmetric, something regular, and with this help, the help of this pictorial reformulation, you minimize. So you want to take, you want to put as much as possible the same label, and then you will get a small number of variables. If you put plenty of different labels, you will get plenty of variables, and this is not what you want. You want to minimize the number of labels. So you can say, okay, I will put exactly the same label everywhere, and you can see what happened. So once you have labeled the triangular prism, then the result, so you will get a labeling for the equation. This will label automatically every tetrahedron. So you only need to consider the labeling of the triangular prism. So you can consider the easiest label possible. You put the same label everywhere and you see what happens. Maybe if you put the same label everywhere, you will get a trivial equation of the form 0 equals 0. So maybe you need to introduce a small variation, etc. But we will see that later. But you see the idea how to minimize the number of variables like that. Okay. So of course, this is for the first step. And then ultimately we want a full sequence. So as I said, it will help also to ultimately to get a relevant sequence of subsystems. So I hope you understood the idea how to get a small subsystem by labeling with as less as possible different labels. So you play with that, and we will prove some results, some theorem about that later in the class. This will be the one of the main theorems of the course. Okay, so now I explained how such pictorial reformulation help for the localization strategy. I provided the idea for that. Now I want to provide the idea of the proof of this TPE equation, how to evaluate in two different ways a label triangular prism by tetrahedron. So I will just provide the idea. So this was the idea for how to use the triangular prism equation. For our localization strategy. Now we will provide a picture due to Dylan Thurston. He put in a paper on graph and topology, illustrating the proof of the triangular prism equation. Of course, it will not be a proof. It will just be a picture illustrating the proof. So the detailed proof will involve a tensor category theory, and in fact, it will be much harder than just this picture. But this picture contains the main idea of the proof. So now a picture by Dylan Thurston. Which is in a paper on graph and topology. Paper published in the journal of some topology, I don't remember, illustrating the proof of the TP. What is very funny here is that, so this paper of Dylan Thurston has nothing to do about tensor category a priori, even if you can find some reach through the topological quantum field theory. But a priori, this paper has nothing to do with the reformulation of Pentagon Equation. And in fact, the reformulation we provided in this paper, which will be covered in this course, was done before knowing the picture of Dylan Thurston. So we were very surprised to discover this picture, which is a perfect illustration of the idea of our proof. So this is very nice. So illustrating the proof of the TPE. So as I said, of course, it is not. So it is just the idea. The picture I will draw, it's just the idea. This idea is far from the detailed proof in tensor category. The detailed proof involving tensor category theory. Category theory is much harder, of course. Okay, so the picture is the following. So as I said, two ways to evaluate the triangular prism. So you start by a triangular prism. So you start by a triangular prism, like that. Tac, tac, tac. Okay. And so the first way we will draw it on the. Let me check. Maybe I should change the order. Yeah, I will put on the left. So the first way to evaluate it. So you should see the triangular prism in 3 dimensions. You visualize it in 3 dimensions as a cylinder with a triangular slice. And then we will reduce the middle. So I will draw, you will understand. So need to visualize. So I will write this after. So I will draw it here, so like that. Two triangles like that. So these two triangles, so this triangle correspond to this two triangle here. Okay. And this edge correspond to the edge here. And in fact, we will draw the edge, we will put some curve. You will understand. To follow the picture of the tensor stone. So when I said we reduce the middle, what I mean is that you want to be this middle as thin as possible. So you make it thin in the middle like that. You compress in the middle like that. Because in fact, the next step is to get something like that. So you compress the middle up to getting a point, and then you get something like that. Okay, so this process to compress, to make the middle part of the geometric form as thin as possible, and then to get a point and to separate it like that will be called in the course, we will call resolution of identities. So this is what we will call so like that. So the process to do like that. Maybe I should not write it here. Let's see. So as you can see here, it will be called in the course resolution of identity. In fact, we will need to add a sum here. But anyway, you don't need to care that much about these details here. In fact, in the Dylan Thurston paper, there is not these details. So process called resolution of identity. We'll call resolution of identity. Because in fact, this part can be seen as identity, and you can reformulate it as a sum of something else. Okay, so we get the the left-hand side of the equation. We were able to evaluate the triangular prism with two tetrahedrons. In fact, a sum of a product of two tetrahedrons. Okay. So the other way is a bit more difficult to draw. Okay. So for the other way, we want three. So how to do that? We will again apply the resolution of identity. So let me draw the picture like that. Something here. So you have that. So two things here, like that. Tack, tack. One here, one here. One here, and something like that. Tack, tack. Okay. So we, in fact, here we already done a resolution of identity, which is not written in the Dylan picture, but you see, you have another one here. We will consider in the next step, and then we will consider another one again. But to understand what happened from here to here, we need to draw an extra picture, which is not in Dylan paper. So let me write an extra picture. Like that. So like that, then so one here, one here, one here. So this is okay. This is exactly what we get before. This is okay. And the difference here, and we will put a curve like that, and we will add a free string inside. And in tensor category pictorial, a free string like that is just has a multiplicative constant. So you can add a free string like that if you renormalize by if you multiply by a constant. So you can do that, and then you apply you will do the resolution of identity here, and you see that you get exactly what you expect from the resolution of identity here. You get these two points as we did here. Okay. Okay, so this is okay, and then you do the same. Do the same again 2 times to get 3 tetrahedron. So you apply it again here. Resolution of identity. So you get this picture. So again, I repeat, this is only the ID. Of course, in the course, we will provide all the details of that, but there's no problem. So, tac, tac. So this one here, here. Okay. And so we make the resolution of identity. So we get this tetrahedron. Okay. And then we do it again here. We'll do it again here to get 2 extra tetrahedron like that. One here. And the one we already have. Okay. So you see the proof we will provide, which will be one of the main results of the course, will provide all the details of how to do all these steps in the tensor category framework. And you see, you finish with a sum of a product of 2 tetrahedron on the left and a sum of product of 3 tetrahedron on the right, exactly as expected here. And exactly as the shape of the Pentagon equation. Okay. So let me just write something I said, but I did not write here. So as the addition, let me write it. I wanted to say the addition of a free string is the same as multiplying by a constant. This string added, this closed string, not free string, closed string is the same as a multiplicative constant. So if you add it, then you need to divide by a constant, and it's okay. Okay. So we are okay with this picture. So let me check the time. Time is it? Okay, so it remains 18 minutes. Okay. So so it's very important to understand this picture. So this picture, the idea is not difficult to understand, at least to visualize. The proof in details will be a bit complicated. So it's good to have this picture in mind. This will make everything easier. Okay. So now so let me mention about the application. So let me write it here. So this course will also consider application. This course will also consider application of TPE, of triangular prism equation, to the classification of some type of fusion category. So this course will also consider application in the classification of three kinds of fusion category. Simple integral, fusion category, in fact, unitary, but we'll explain the details later. Multiplicity-free, So the fusion coefficient I will explain after that should be 0 or 1. Another kind, near group. So the classification of simple integral, multiplicity, or near group fusion category of small rank and or small enough Frobenius parent dimension. So we will, as I said, we will recall the definition of fusion ring. It is not long. So then we will understand what I mean by rank, by Frobenius parent dimension, etc. If we did not see that before. Okay. So in this course, we will mainly focus on the first type of fusion category, simple integral. But we will also briefly consider the second type. And at the end, we will finish the course. The end of the course will be dedicated to complete a work in progress about the application to a near group. So there is a work in progress which is unpublished, not yet published. And the end of the course will be dedicated to finish this paper. This is the big challenge of this course, in fact, to teach research which are being done simultaneously in some sense. Okay. Okay. So small. Okay. So as I said, I will repeat. We will mainly focus on the type 1. So in fact, we will be more specific. It will be simple integral, 1 Frobenius, unitary fusion category. 1 Frobenius. So I will explain this notion later. Then we will briefly mention the kind 2. And finally, the end of the course will be dedicated to complete a work in progress. Will be dedicated to 3 requiring to complete the work in progress. So this work in progress has the same author as the paper we consider. So Zhengwei, myself, and Yunxiang Ren, the same author. As above. Okay. So this is the main point, the main application. But in fact, so the localization strategy, it is not the only tool we will use for the classification of simple integral fusion category. We will need three other tools, in fact. 2 of them are included in the paper we cover, and 1 of them come from a previous research paper. So the 2 will be so among these 3 other tools, we will provide details of 2, and the last one we will mention it without details. So for the application 1, we will also need to consider our, when I say our, I mean done by me and my co-authors. So first, the sure product criterion, which was later renamed in another paper, and primary criterion, and generalized. So sure product criterion, renamed in another paper, generalized as n primary criterion. In fact, the sure product criterion corresponds to n equals 3. But even for n equals 3, the n primary criterion is stronger than the sure product criterion in the non-commutative case and in the when the fusion data is you have some missing data. But I will mention that. So this is the first tool we will need. So I will not provide the details of this one. I will just mention without too much details because it's a complete other paper, and in fact 2 other papers. So our proof next of one conjecture about Frobenius-Schur indicator, our proof of Wang's conjecture about Frobenius-Schur indicator, Frobenius-Schur indicator. So this is in the paper we cover. And the last tool is our zero spectrum criterion. So we will prove a new criterion, a new categorification criterion called zero spectrum criterion. And in fact, there's also another one called one spectrum criterion, but we will see that later. Okay. So ABC. A, B, C. Okay, so as I said, only B, C will be covered in details. Because contain is a paper we consider. The A without details, but maybe we'll provide details in some next semester. I don't know, maybe I will do a course about that in some next semester, but not this semester. Because contained in the paper we consider, we cover, and so A will be mentioned without details. Because contained in another paper with an extra author, in fact, contained in other papers, in fact, two papers. One paper by Zhengwei, myself, and Yunxiang, and one other paper with this one, Zhengwei, myself, and Yunxiang. So there are two papers. One is about sure product criterion, and the other is a generalization called the N category, the N primary criterion. Okay. Okay, so for the last 5 minutes, I will start to recall the definition of a fusion ring and fusion category. So more details for fusion ring and less details for fusion category. So as I said, you should go to the last semester material. So now, we will recall the definition of a fusion ring. So this fusion ring, this will be quick because the definition is quick. And fusion category. So in details for the first and briefly for the other. In details. And here, briefly. So as I said, for more details, So I covered this definition 4 times the last 4 semesters. So I did it. It is enough. So for more details, see. Last semester. Review part. In fact, I put the link of the web page of last semester in the web page of the current semester course. In the prerequisite, I added the link to the previous semester web page when you can find the material, the slide, and the video. So briefly, for more details in last semester review part, slide and video. Slide and video. and EGNO book. So Ettinghoff, Gelaki, Nikšić, Ostrić, book called Tensor Category. Okay. So definition. I will define what is a fusion ring. And before that, to do that, I need to define what is fusion data. Definition. But I will not, I will just write the title. In fact, we have no time to write more details. So a fusion data. A fusion data is, and in fact, what I just want to write for today, so we will finish that tomorrow. But for today, I just want to write the following. Slight generalization of the notion of finite group. Of the notion of finite group. So we have the notion of finite group, the finite set with some axiom. So fusion data is a finite set, right? 1, 2, up to R, satisfying some axiom with, we have an evolution which we generalize the notion of inverse, an axiom, associativity, unit, inverse, etc. Generalizing the axiom of a finite group, but we will see that tomorrow. So this is, so I will do that tomorrow. So end of session. Okay. So we will see you tomorrow. So again, if you have questions, you can ask questions in the WeChat group, or you can ask questions in comment of the YouTube video, because this video will be also put on YouTube. So I will send the slide and the video on the WeChat group, and I will also send the video on YouTube. So you can ask questions on YouTube, you can ask questions on the WeChat group. You can also ask questions during the course, in fact. If you have something you want to clarify, you can ask a question also during the course. Okay, so see you tomorrow.